Our second speaker of the day is Viraf Mehta from Göttingen University, and he'll be telling us about cosmological constraints on the KS Axiverse. Take it away, Viraf.
Okay, so thanks a lot, Cody, and also thanks to John for organizing these seminars and keeping us all in touch during these difficult times. I hope everyone is safe and healthy. So also thanks to Mehta, who essentially presented the first half, or at least gave some of the ingredients that I want to use during my talk. So Mehta presented, at least in the first half of his talk, how this algorithm that they've designed can obtain various data about cycle volumes in orientifolds in 4D toric varieties. So the question that I want to ask is whether the physics related to these can be constrained in any meaningful way. So what I'll do, so I'll first start with the take-home message, which, screen. In that it seems, or yes, it would seem that using the phenomenon of black hole superradiance, we're actually able to put some constraints on the underlying string geometries. So what I'll do is during the course of my talk, I'll present the rest of the ingredients and then the recipe that we followed in order to generate this plot. And what I'll do also is try to quantify how large a pinch of salt one needs to take in order to consider this as a kind of final exclusion plot, i.e. what kind of assumptions were made in order to generate the data that led to this plot. So here's the outline of my talk. I'll finish off the introduction to the Cosmological Axiverse and specifically discuss the ingredients that we require in order to do some physics. This is heavily based on the Cornell Group's paper from 2018, and also more details can be found in their paper from last month. Then I'll discuss some the physics that we'll use to constrain the Axiverse, and then I'll put these two together and show how I generated this plot. Okay, so for those that are either too young or too stressed to remember any physics BC, that is before Corona, the Axiverse has been around for quite some time, but it was first given its name by Asimina and her collaborators back in 2010. So they postulated that due to the vast number of KK zero modes arising from the compactification of higher dimensional forms, some of these zero modes would appear in our universe as very light fields, or so with some mass or potentially massless. In addition, in addition to having several fields appear, they also span a very large range of masses because of the fact that their mass is either inversely proportional or exponentially suppressed in terms of the volume of the cycles around which these higher form fields wrap. And so because of the fact that we have these varying volumes and a huge number of fields, you can essentially fill the spectrum from the Hubble scale to the string scale. So in order to generate the mass spectra for our ALP systems, what we'll need to do is bridge the gap between the calculation that Mehta presented and generating the physical axion data. So as I mentioned, the Axiverse derives from the multitude of ALP sources in a given string model, and the vast range of volumes these fields will wrap. So the masses of our axions in particular, or our ALPs in particular, are exponentially suppressed. That is, they're proportional to the exponent to the negative e to the minus of volume is essentially gives us a naive estimate of the mass. So the particular ALP sources that we will consider or C4, the KK0 modes of C4 forms. So that is the number of fields that are wrapping 4 cycles. And this will actually correspond, so this actually corresponds, therefore, to H11 ALPs appearing in any particular setup. Now, as the questions alluded to earlier, we now have access, in principle, to large H11s, which was previously, at least, unfeasible. So what we do specifically is consider Clavier threefolds in 4D toric varieties, as outlined by Mehta, and we choose our Kähler form J such that we're at the tip of the stretched Kähler form. Now, as Mehta outlined very nicely, the various conditions that for the volumes of the Kähler form, but so specifically the one that puts us at the tip, or the condition that's most important, is that all cycle volumes within the stretched Kähler cone are greater than or equal to 1 in string units. Now, of course, because of the relationship between the volumes and the masses of our ALPs in this sector, we'll see that increasing, or we might see, if I've got time, increasing the minimum volume actually decreases the maximum ALP mass in this sector. Okay, so let's concretely define our ALPs. So they are indeed written here, and the different ingredients that we require in order to write down an effective Lagrangian for the ALPs are presented here on the slide. So what we have is the Kähler metric, which, as we can see, is dependent on both the overall volume of the Clavier and the cycle volumes, tau. And so essentially, in order to construct the Kähler metrics within the stretched Kähler cone, we can sample over tau and V. The details of the sampling algorithm were outlined in the paper last month, and I would very much recommend that you read it if you're interested in the details. Now, calculating Q is less straightforward if you define that finding K is straightforward. So calculating Q, in fact, is currently beyond, fully calculating Q, that is currently beyond our technological, both analytically and computationally, beyond our technological reach. Because in order to compute these, what we need is full knowledge of the fermion zero modes on the divisor that supports the Euclidean D3 branes, which are the leading contributing instantons in our case. Now, Liam and Cody and collaborators showed that in a paper, I think in 2015 or 16, that a good approximation is to have all prime effective toric divisors contribute to the Euclidean D3 brane superpotential, although ultimately, of course, some of these divisors may not contribute. So, in fact, once we've fixed our polytope, once we've chosen our polytope, then this means that Q is therefore determined. So we can write down our charge matrix once we have chosen a particular polytope. Now, so far there has been no evidence to show that this is either insufficient or an inaccurate reproduction of the charge matrices. But of course, it would be it will affect the physics, the underlying physics. And then, so once we've got K and Q in hand, of course, lambda is easily computed, and so as Mehmet mentioned, now generating this underlying geometric data for our ALP potentials is, I would say, fairly fast. And so we now have access to large H11 geometries, as I briefly mentioned. And so what we're able to do now is take this unprecedented first step toward constraining large sets of geometries using physics. And the particular physics that we're going to use is black hole superradiance. Just to put black hole superradiance in some kind of context, so here I have presented an ALP log scale of ALP masses. This cartoon essentially shows what various experiments and bounds there are, or there can be, on different very light and ultralight ALPs. There's an additional, there's a third exclusion window using data recently taken from the Messier 87, which we also will include in our analysis, but isn't on here because the data only appeared this year. So what I'll focus on is indeed this black hole superradiance and how we can interpret black holes as high precision particle accelerators that can probe these extremely light mass regions. So the phenomenon of superradiance in general from rotational bodies is a feature which can occur in systems that present a dissipating surface with a non-vanishing angular momentum component. So in the context of black holes, Penrose first postulated this. It goes like, so for a spinning black hole, that is a pure black hole, to an outside observer at infinity, the black hole has a region outside of its event horizon, known as the ergo region, inside which the inertial frame is being dragged so fast that any normal matter that enters this region cannot remain at rest to our external observer. Namely, what this means in terms of the physics is that the time translation killing vector actually becomes space-like. And so if there is a bosonic field within this region, the killing energy density can actually become negative. And so what our observer actually sees is a growth of the bosonic field as an extraction of angular momentum from the black hole. So this is known as the superradiant instability. Now, because of the fact that we're considering bosonic fields can essentially reside in degenerate energy levels. And so what happens is, in principle, you can form a kind of gravitational atom around a black hole. The fine structure constant of our gravitational atom now determines the efficiency of the instability. And the fine structure constant is essentially dependent on the two scales in our problem. That is the size of the black hole, which gives us the mass, and the Compton wavelength of the bosonic field, which also can give us the mass of the bosonic field. So when the Schwarzschild radius of the black hole and the Compton wavelength of the boson are comparable, superradiance is actually maximal, and will run until the superradiance condition here at the bottom. Is no longer satisfied. So omega A is just the wave frequency, that is, it's essentially inversely proportional to the wavelength of the ALP. And omega plus is just the angular velocity of the black hole horizon. And this is dependent on the size of the black hole and its spin to mass ratio. So as I mentioned, this gravitational atom, so we can have these kind of energy shells around the black hole, and these energy levels can actually act as the mirror in Tucholsky and Press's so-called black hole bomb scenario. And so what happens is you get an exponential increase in the filling of this of the bosonic field energy levels, and so this instability is therefore exponentially increased. It's not just maximized, but it's also exponentially enhanced by the fact that this mirror appears. So I think this, you can see the animation. So so the data that we require from the black holes, the data that we actually measure in order to constrain our ALPs, is the mass or the size of the black hole and the spin. Using that data, we can actually derive a strict limit, i.e. the spin down exclusion of the black hole. So here, this animation only contains a subset of the black holes that we actually use in our analysis. These are in fact the stellar, 4 of the stellar mass black holes. But essentially, I wanted to just present this animation to show how the total exclusion over a given mass range is essentially how you can see how it's made up by the various different black holes. In actual fact, we have 15 stellar mass black holes, and now we have 9 supermassive black holes, which includes the latest results from Messier 87. So using this black hole data, the ALP masses excluded, as I mentioned, fall into the 3 windows, 2 of which are on this plot, and you can see outlined with the black line. And the last one comes from, as I mentioned, Messier 87. This is a small window, somewhere between 10 to the minus 20 and minus 21. When we apply these limits to our data, just to note for when you see, or if you remember the exclusion plot, but we'll see it again at the end, just to note, we use the 95% confidence levels for all of these black holes. Okay, so now that I've presented the 2 different ingredients, what I will do is look at some how we can apply these constraints to the Cosmological Axiverse and get back to generating that exclusion plot. Okay, so what does a typical axion, what does a typical ALP potential look like? Well, essentially, once we write down our potentials, these are potentials with H11 ALPs generated by P instantons, where in general, or at least in our data set, P is much larger than H11 in a majority of cases. In a typical potential, there are many deep valleys, and the potentials can also be extremely noisy. So because of this, in order to calculate any kind of physics, one would hope that you could find a minimum. So, or actually, desirably, we would find the minimum. Because of the fact that these potentials effectively look very noisy, despite the fact we can calculate the gradient, what we do is we actually use black box optimization methods. And so in combination with, because of the fact we're using very tiny numbers, in combination with multi-precision tools and a Python package from the European Space Agency, we were able to minimize at least the subset of potentials, or the subset of ALP potentials that I will present the results for in the next couple of slides. Now, once we acquired a minimum, we wanted to test the quality of it, and in order to do that, you simply repeat the calculation, and we also computed the Hessian eigenvalues at the various different minima, if different minima were found, in order to check that these all matched. So, having found the minimum in the string basis, we can then transform all the quantities through the canonical basis to the mass eigenbasis. And we end up with a Lagrangian that looks like this. I've grayed out the quartic coupling part of the Lagrangian because for now I'm not going to talk about that. However, so just taking the quadratic part of the potential, the masses now are just the eigenvalues of n. Okay, so I've grayed out, like I said, I've grayed out the quartic coupling, but the reason that I've put it on the slide is so far I've been discussing black hole superradiance as a purely gravitational phenomenon. This is not strictly true because of the fact that at some point self-interactions will kick in and the Bose-Einstein condensate will dissipate, or it potentially not form. And so you won't actually get any, so essentially they'll decay faster than they will be able to extract energy from the black hole. So for ALPs, this can be quantified by F, the decay constant of an ALP, and the plots that I showed earlier, the exclusion plots for the black holes, are only valid when F is greater than 10 to the 14 GeV. Now, the question is how we calculate F in our string construction. Well, I won't discuss that in detail, although it's probable that I'll get a question about it. What we can do, rather than, so it's difficult to obtain actual numbers for F, but what we can do is we can have a look at what patterns we see in larger H11 geometries. That is, a naive estimate of the size of the fundamental domain is essentially proportional to the eigenvalues of K. This is kind of just a very back of the envelope calculation, and I mean but the details of this of how you can get this bound on the fundamental domain, it actually is in a very nice paper by Liam and Thomas Bachlechner and Cody, I think 2015. But essentially, so we can actually look at the patterns. And so what we see is, because naively the size of the fundamental domain will determine how what F we can extract. So essentially, as the as H11 grows, as the geometries get larger and the multi-ALP systems get bigger, what happens is, or what seems to happen, is the decay constants decrease. And in fact, after, let's say, I don't know, around H11 equals 100 or so, it looks like, I mean, just from this naive estimate, that these geometries perhaps one would require calculation of the self-interaction in order to impose any black hole superradiance bounds. Now, calculating self-interactions, of course, would give us a proper physical F. This is not something that I will present. However, it may well appear in the final paper that should appear in a couple of weeks. So an easier way to see the trend for the subset of data that I studied is by looking at this plot here. So it's clear that as H11 grows, the size of the fundamental domain, or at least a naive estimate of the periodicity, decreases. So we may well expect this for any physical F that we can derive. Okay, so we've crossed most of the hurdles. Now what we can do is throw our large data set, that is up to H11 equals 50. So this is approximately 50,000 different axion potentials. We can throw it at a cluster, and several CPU hours later, it can tell us something about the mass spectrum. So for starters, the fraction of massless ALPs is actually quite significant. So here, the two different patches are essentially float 16 precision in orange. That is float 1 to 28 for those who are in bits over this. And the pink region is the fraction below the Hubble scale, i.e. those that would be rendered essentially physically massless. Okay, so that's all well and good for the massless sector, but I mean, it's the massive ALPs that we care about. And indeed, in this bottom plot, I've only included massive ALPs in our geometries, in our spectra. And in the top one, this is the full spectra, just to see a relation of how the overall spectrum is dominated by massless fields. Okay, so there are several features on this plot that I could go into some details about, but I think I'll save most of them for the discussion if people have questions. Perhaps the first obvious thing that people notice is that essentially it looks like the largest mass is constant for all of the H11s that we studied, and indeed this would naively be the case because of the fact that the smallest volume is less than or equal to 1 in string units, essentially the definition of our stretched Kähler cone. Or the condition for our stretched Kähler cone. Okay, so just to give you an idea as to the distribution of the massive ALPs, what you can see is that there seems to be a peak in all cases at around an EV. Using essentially, this is just a KDE approximation of the binned data that I just showed. And in future, it would be very nice to try to use the distributions of, let's say, smaller H11s in order to try and study larger H11s. And so here, therefore, we have the masses, and I can re-show this plot. So now that we've got the masses and we've got our bounds on black hole superradiance, we can apply both the cuts from supermassive black holes and stellar mass black holes. Because of the fact that we don't want to consider self-interactions yet, we fixed F to be the string scale, which in our case, we've just set to the reduced Planck mass. So what this plot actually shows, because of the fact that we've nullified self-interactions, is an absolute upper limit on the exclusions for black hole, for the exclusions on these various geometries. Let's say that we took our naive estimate of the Fs as physical Fs. Well, as you can see, as these Fs, as we saw in the plot, the Fs are decreasing, and so the this general trend of increasing exclusion as H11 increases will actually turn over. And indeed, this would also be expected even if F was always, so in fact, there are two things that can contribute to this curve turning over. As I mentioned, self-interactions will kick in, or of course, as massless fields dominate, the massive spectrum of the ALPs may well not appear to cross through the black hole superradiance bound. And so there may well be just one massive ALP featured at the smallest cycle volume, and then there may well be a desert to massless axions. So these two different things can combine at large H11 and therefore could at some point turn this curve over. But this one is the one to remember. Okay, so we've come complete circle. I showed you how we use the string data to generate the various multi-axion systems and then compute the mass spectra for a subset of these geometries, namely up to H11 equals 50. We then applied our black hole superradiance constraints in order to generate this exclusion plot for string geometries. Follow-up projects to this work, which would, I think, be very interesting to the wider community, would be that, so at the moment, the code is fairly well optimized and can probably handle with enough cluster time or with a bigger cluster, which I'm applying for access to, could well handle up to H11 equals 100. The question then would be, okay, if you're going to stay at the tip, is there a possibility if you venture into the Kähler cone that indeed you can bring the peak, if you notice the peak was around an EV, can you bring this peak over the black hole superradiance bounds? And if there's time, I can show what happens when we venture into the Kähler cone. And then the question is, now that we have this data, now that we have this very nice ALP data, are there other physical constraints that we can apply? Alongside this, it would be also nice to explore up to H11 equals 91 and try to get some handle on what ALPs may well be produced there. Of course, this is a long-term project and will take us quite far into the future, maybe even into the after times. So thank you very much.
All right, thank you very much, Viraf, for the very nice talk. Let's all thank Viraf using our clap emojis. Are there any questions for Viraf? First question is from John.
Let me see if I can you hear me?
Yeah.
Yeah. So I was wondering about, it seemed like in the plots of black hole mass to black hole spin, there were basically two different regions. There was one that was like lower mass that was coming from like LIGO, and then one that was higher mass that was coming from like galactic stuff. How much of your constraining power is coming from the LIGO data set? Because there you had essentially like enormous error bars in the spins of the black holes. And so you'd expect not to be able to use, you'd expect that that does not contain very much information about excluding these types of fields.
Yeah, in fact, the black holes that we use, the data for them is here. I'm pretty sure that any ones that come from so it's these ones here that you're talking about, the stellar mass black holes, right?
Yeah.
That are from LIGO. So, I mean, so the regions, I mean, I'd have to look at the plot specifically, but essentially, even if you ignore these ones, you can still apply pretty stringent constraints on a smaller mass window, agreed. But maybe the best place to look is a paper that appeared, I think, last week by Matt Stott, our collaborator. He's just written his thesis on constraining ALP masses with black hole superradiance, and he actually goes into a lot of detail on the modern techniques that are used for this. So I would definitely recommend glancing through that if you have a chance.
Okay, our next question is from David.
Oh, I think you're on mute.
Yeah, David, I think you're muted. Well, yeah, David, if you can hear us, we're not getting any audio from you. Nothing. Do you have headphones connected? Oh, wait.
Yeah, that's me. Maybe I can switch on like this. Hi. Yeah, very nice talk, both of you actually, Mehmet and Viraf. I enjoyed listening. Now, maybe I'm a bit slow. Maybe this is because I didn't really work on this, but can you just explain me again? I mean, you get the distribution of the axial decay constants from the distribution of cycle volumes, assuming the stretched Kähler cone, right?
Mm-hmm.
what is it when you have certain data on the black holes? I mean, like bounds on the spin and mass and so on. So how does that really? Why do you get these distributions that you had there? I mean, I somehow I missed the link there. I mean, I really, it's just from maybe I'm just not understanding. I mean, I just want to know what data on that certain black holes with certain masses for certain spins are not observed or are observed are then basically putting limits on the distribution of axion decay constants.
Right. So essentially the decay constants kick in or make self-interactions dominate. And so essentially right now, the constraints that we've used, there will be no self-interactions because of the fact that we've put the decay constant at a very large scale. There's no, gravity will essentially dominate. Gravity is the scale that dominates on this level. But once the decay constant decreases, then the self-interactions of the ALPs will begin to dissipate the bosonic cloud.
Ah. And the cell interactions go up when the F gets smaller, right?
Exactly.
When the F gets smaller, they get up because it's okay. This is, I see, this is like the fourth derivative or whatever of the cosine potential. So they go like 1 over F to the fourth or something like that, roughly.
Exactly.
I see. So they get bigger and then therefore you lose them quicker. And that means that for those Fs, you never build up enough axions to ever produce the superradiance effect.
Precisely.
And then therefore you would, so then you turn this around and then I see. Okay, thank you. Thank you. This is very nice.
Yeah.
Okay.
Okay. Well, if there are no further questions, then let us thank both of our speakers again for the excellent